So today our lesson is about recursion. What is it? You know that code can be organized with functions. For example, function A can call function B. I'm drawing this like linked graph with functions as vertices of this graph. So if function A inside it, maybe with some parameters, I'm not interested in parameters now, somewhere in code function A calls function B, then it is drawn by me with such an arrow. Okay, so but function B can call some other function, function C can call some other function. Okay, it's okay. B also can call function D, and it can call some function E. E can call function F and G. So it is the way how we organize code. We split our big algorithm with very long conclusions, expressions, and some hard logic to small portions, call them as functions, give some names with understandable, readable names, but our question now is not about organization of code. The question is, can there in the tree, in the graph tree of functions calling themselves, can here be loops? I'm not talking about such situations, because from graph theory it's not a loop. It's not a loop because you can't return to vertex E. There is no such way. But can function F call function E, for example? So E calls G, G calls F, but F can call function E. The simplest situation is this. For example, I will erase this arrow. Can function D, for example, call itself? Can the function call itself, or it is impossible? To solve this problem, to understand can it be done or not, we can just check it with interpreter. Let's check. Let's open interpreter and start it and ask what will be if we just call function from itself. To see that function is working, I'll create function just here inside REPL. Okay, def foo, no parameter at all, and then print something, hello, and then call function foo from itself. Okay. Yes, I can create such a function, but what will be done if I call this function? Oh, I can see many hellos here. Hello after hello, and it works and works. Oh, and what is now? Now there is an error. So situation is strange, because syntactically it can be done, first of all. Second, it works. Third, it works with some bug. Error conclusion here is that recursion error, type of error is recursion error, and the result, maximum recursion message of an error, maximum recursion depth exceeded while pickling an object. Maximum recursion depth. Why depth is mentioned here? Because when function I'll return to ABC. When function A inside its body somewhere, I don't want to draw really draw block scheme here, but I will just draw a star sign as point of execution of function. Function started its execution. Why it's not really mentioned somewhere from main module, it was called, but somewhere inside function A there was call of function B with square braces, not square, with round braces, and then it means that function B execution started. So I will draw star sign here, and time of execution operations time, global time is going here. Time axis is from up to down. Okay, so commands of function B are executed, but function A is not executed at the same time. It just waits for the finish of function B. When function B dies with the result, I mean not really die, but die with the result, return, correct return of result. But this end of execution means that every resource of function B, what are resources of B? Variables. Variables. And first of all, names. Names are main interesting thing. Scope of names. Space of names. Namespace. That is what was created with call of B. Okay? So namespace of function gives it a way to work with space of objects. Okay, so here in C++, there is a term namespace, but here in Python we'll better work with scope of names. Scope, like scope of ice cream, some portion of names, and each call of function creates new scope of names. In Python, I mean. So new names can point to new objects if they are calculated. But now you can see that function B, I'm not writing now bodies of these functions, but you can imagine that on some instruction return inside function B, it means that the execution line, execution flow is returned to function A, and function A continues to work from the same, exactly the same position where function B was called. If it was called in instruction x equal B braces, then it will continue with assigning to x something definite what was returned by B. For example, if B returned here 5, then our function A will assign 5 to x, because it has the result, already calculated result of function A. But now I'm interested in execution flow. So function A is waiting for result. You see? That is called synchronous sync call. synchronous call. Okay? It means that calling function, caller, is waiting for the result and does nothing during its waiting. Okay? When function B calls some function, it can be done, yes, of course, and it means that execution of function C starts. So new scope of names for function C is created. Then names are destroyed with the scope itself, scope of function C during return is erased. So all local variables are destroyed with scope of names which was created with calling of function C. Okay? But now, what if some function starts? So you can see that their functions wait for other functions, call them as their slaves or maybe workers. Oh, my slave, do this work for me, I'm calling you and I'm waiting for the result. Okay, so and host is doing nothing during waiting, but he is also somebody's worker and was asked to return some result, and he's obliged to finish and to return something to previous function, otherwise program will not work and algorithm will be broken. Okay, so but what if some function, during this process of calling functions with which are calling functions in Russia, we have a fairy tale which is called Repka. I even have figures. I can't remember how it's called in English. Repka. Here in this tale was grandfather seeded this plant, and it said grow big, grow hard, and it grew up very big, and grandfather started to pull it, and he pulled and he can't pull it up. Then he called for grandmother, help me please. So we can imagine that this grandfather is a function, and this plant Repka asked him to pull me out from ground, and he started to pull, and then he cannot pull it out and called for grandmother. Grandmother understood that the task is more than she can do with pulling. They pull and cannot pull it out, and she called granddaughter. Granddaughter called dog called dog. Maybe it's better to draw on board because it's not convenient for me to all. So grandfather pulled this plant from ground, tried to pull it out, but he cannot do it. So he asked his wife, babka, grandmother, to help him. She is but she cannot pull it up. She cannot solve the task without her granddaughter. Granddaughter was asked to solve task, but she can't do the task. She cannot apply force of such magnificence to help her grandmother. So she called a dog, and a dog started to pull daughter. Dog understood that work cannot be done without a cat. It called cat as a function, of course. And cat called mouse, mouse. And mouse called nobody. And its main interesting feature, the tail ends when mouse starts to pull cat. Cat pulls dog, dog pulls granddaughter, daughter pulls grandmother, grandmother pulls grandfather, grandfather pulls this plant, I can't remember, repka. And they could finally pull it out from the ground and ate it. Okay, so we can see that here is delegation of some task, and each function in the middle, each hero in the middle for us, it's just a function, cannot solve the task by itself. However, and it looks like going into depth, going deeper and deeper, because task is subdivided to some some lesser tasks. Task which is asked by another hero is easier, because maybe grandfather was asked first of all by plant to apply force of, for example, 100 of newtons. It's not very big force, but 1000 of newtons, but he had only 500 of newtons. It's about weight of 50 kilograms. But he can't solve the task to apply 1000 of newtons, and he asked his grandmother, help me please, and give me additional force of apply to my back additional force of 500 newtons. It's like a task which can be put here inside parameter. Okay, but grandmother realizes that she can apply only 300. It's like weight of 30 kilograms. Okay, so she needs 200 of newtons additionally, and she asks her granddaughter to apply such a force to her back. Granddaughter has only force of 100 newtons, and she asks her dog to help. Her dog has only 50 newtons, for example, and there is lack of 40 newtons, but 50 newtons, but cat has only 40 newtons. So cat asks mouse to apply force of 10 newtons. Not so realistic, really. Okay, 49 49 newtons and 1 newton only. But the main interesting thing is that mouse doesn't call anybody. Mouse just solve the simplest task by itself. Task the problem which was given to this function is so simple that this function can solve it without delegating any subtask to any other function. Okay? And this process of delegation and process of calling another function is like going into deep. Okay? Deeper and deeper and deeper, but this case is the final case. Final case of the recursion. So, the term recursion, what is it about? The recursion is, it's not an algorithm really. Recursion is class of algorithms. It's like way of solving task with decomposure of initial task to subtasks. Decomposition. You have some task, not function, some task. And this task is too hard for you to solve it. And you are trying to decompose it to some parts. And if you can see that some subtask is very, very similar to the task itself, if it's just like task itself, but simpler. Here, the task was to pull. They were to pull each other. Okay? And the only thing which was different is force. Force number of force power which was to be applied. Okay, so subtask differ from task of the function itself only by scale. So if subtask is just task but simpler, then this problem can be solved with recursion. Recursion is a way of solving task with programming, of course, when you cut and delegate subtask from your task, from task of the function, and delegate this subtask, which is very similar to the task itself, to who? Who will be responsible to solving subtask, which is very, very similar to the task itself, but with smaller scale? The function itself. The function itself will solve this similar task for the function. So, it looks like me calling myself to solve some subtask. Then me understanding the task is too hard and somewhere in the middle of solution I want to call myself once again and waiting for the result. Let's return to our first formula. Each call of function creates new scope of names. Not each function has its scope of names. No, it's wrong. Function doesn't know. not really correct, because function has some scope in Python, but normally we don't use it at all. Normally we don't use functions scope of names, so let's forget about it. But function has attributes in Python. I don't know about it in other languages. But call of function creates new scope of names. So with this call, we start execution of new function instance. You should understand difference between application like notepad.exe. I know that Microsoft Windows hides from users that files have extensions, but execution files are called something.exe, exe. So executable files. Calc.exe, notepad.exe are just files. They are, like I already told you on our first lessons, that files are just information. You can just copy them, destroy them, delete them, modify them with some editor, text editor, for example, hex editor. Okay, but if you execute file, it creates process. Process is like a live substance. It can do something with some resource. It has some resources, some processor time, some memory to store its variables. Okay, that is the difference. And one executable file can produce many different processes. Okay, that's why I can call Python many times. I can open many windows of idle process, and my operational system will create several windows. Each one is different. Okay, and it's normal. And here inside the program itself, there is also difference between function as an object and function as living object, as executed part of program, already executed. So each call of function creates a new scope of names. Okay? So really, each exemplar, each instance of function is different, and it has its own variables. Really. So let's create such a function here. Def. Oh, also about the mouse. About the mouse. Mouse is the final case. Other are recursive cases, but mouse is very important. Here, in this example, in previous example of function, I just hadn't such a mouse, because my function foo was calling itself too many times. It was to go to infinity, but I should somehow finalize execution, because here was no any real task, or maybe task was the same scale as the initial task. It's not normal. Subtask should be easier than the task itself. So task should be parameterized. It's needed, some parameter is needed here. Okay, so maybe this parameter is depth, глубина, depth. So hello, and here I will print depth current, depth is, and print depth. But here, when I'm calling function foo itself by itself, I should think should I call it or not? Because if I'm a mouse, if I'm the final case of recursion, I can't go to recursion. I can't call function. I can't call myself. So I should, it's obligatory to use some constructions to stop recursion here. To sometimes call, go to next level of recursion, go deeper, sometimes stop and just return something back. Okay. So if I return none or just finish function, then it returns none. It just calls stops execution. So here I will use Python. I will use the conditional operator if, and I'll stop if depth is more than 10, for example, or more than 9. Oh no, now I'm not stopping recursion here. I want to call function if depth is lesser than 10. So 10 and more are I want to put foo here inside conditional operator. Okay, so foo is called only if depth lesser than 10. So I can call this function from 0, for example. Well, it's not true. From 1, for example. Oh, where is the problem? Problem is here, because with call of function I need to provide it the task, and the task now is depth of execution, depth of callings. But now if I call function with any parameter, then it will just produce my current depth is 1, and it's going on and on. I will not wait for the finish because I know that after some time, after 900 and some 99 calls, it will stop with the recursion error, maximum recursion level exceeded error. But what I want is to give this sub-called function some subtasks which is easier. What means easier? Now easier means that depth is increased, because stop of recursion is when depth is equal or above 10. So I will give this next function, I need to just repeat its definition and correct it with such instruction: depth plus 1. This task is different and it is easier. Yes, number is bigger, but task is easier because it's closer to the final case of recursion. So easiness of task is measured not only by numbers, not only by time consumed by this recursive case or final case. No, really final case can take much time. For example, in checkmate, in chess, for example, in chess, final case is very time consumable. In algorithms of artificial intelligence in game of chess, final case is not so easy. Okay, I see that we have to restart our conference. Please wait for link in Telegram channel. Okay, So let's continue. I told you that task, a subtask inside recursion case of function, case when function goes to recursion deeper, should be with simplifying subtask. And subtask should be simpler than task itself. So it's not easier to go to depth -1 case, because it will not lead me closer to the final case of recursion. Okay, and when I call foo5, then this number is going lesser and lesser, but more far. It's too far to achieve final case, because final case is above 10. Do anybody has questions? No? Jeremiah, hello.
Yes.
Okay. But here, oh, I'm sorry. Here I need to go to case depth +1, and that's my idea. I call foo with parameter 1, and it just goes through 1, 2, 3, 4, 5. Look, what if I put here else case and print oh la la here? What will be done? Foo 1, 1. Oh, holala. Holala is a case of my mouse, my final case of recursion. Okay? Where function decides not to call itself, decides by this condition, not to call itself, but to print holala. Okay? However, it already printed its this string with depth equal 10, so I can see this. Okay? It looks very similar to very simple loop construction. Not loop construction, but result of looping with for loop, for example, maybe with while loop. So the main question is, oh, what for this recursion is? We just created some new looping form of loop, so it's not necessary to use recursion. Yes, being more being more accurate, I should say that each recursive version of algorithm can be rewritten without recursion, with only loops, especially with while loop. While loop is the most universal one. Okay, so while loop can be used instead of usage of recursion, but there are many cases when recursion gives us better understanding of algorithm, better, more readable way to write algorithm. And first of all, if you see that your algorithm is recursive, then try to just use recursion. Okay, but this task to print some numbers is not the case where recursion is to be used. It's too simple, and only loop can be used here. But my idea was to show you how recursion works, first of all, and we had something like loops, yes, without any while, without any for. But interesting thing can be shown here. Here, when printing holala, I can add to function some bad construction. This construction will be 1 divide 0. I want to produce an error here, to produce some okay, this code can be compiled. This code can be such function can be defined. But what will be during execution? Oh, look here. We have traceback, and this traceback show us that error is foo1. Then foo depth plus 1, foo depth plus 1. Yes, in line 4 several times. Previous line repeated 6 more times. So here I was inside function, inside function, inside function. So there is such thing as call stack. Call stack. Call stack. Stack is some type of queue. Call stack is stack used to manage such calls of function when one function calls other function, because to return to the proper place you should know address, particular address in code where to be returned, and the addresses, the code instructions addresses are stored inside call stack. So when first function is called, then returning address should be stored inside call stack. When second function wants to call third function, then to have execution back again, to have execution flow back again in synchronous sync call, in synchronous call case, B is waiting and A is waiting for B, B is waiting for C function, and B should catch flow of execution after C ends its execution. So when calling from B, calling C, then B should store address inside call stack. B return address is here. Here is return address of A. So when execution is inside C instance of C function, then here in call stack there are several addresses of execution points where to be returned after return. Okay? And if somewhere in deeps of execution, somewhere here occurs an error, occurs an urgent error, exception. Exception means some error which doesn't imply any variant of normal execution. Execution cannot be done by regular way. So D cannot return anything to C. And exception starts to break program. No, to exit from program. It somehow flies. it's like chief of, for example, chief of an organization. It's his team leader. Team leader asks for a task solution to, for example, programmer. Programmer asks its junior programmer, and junior programmer took his notebook, started coding the code for his programmer. Programmer then will a complete solution return to team leader. Team leader will return it to manager. But let's imagine that this junior took its notebook, and here from notebook some octopus is some alien starting, and he can't complete his task and return some code to the programmer. He's just running and crying, ah! Okay, so exception is something so abnormal that normal execution cannot be produced furthermore. Execution cannot be completed. So exception just gives us current state of call stack. It's needed for us as God of the situation to analyze what happens. So we can see this trace back. It's really call stack reversed in reversed order. So now we can see the last state on the end of this traceback, and these tracebacks sometimes are very long, because functions like to call other functions, not themselves. Recursion is not so frequent situation of solution, but here I produced division by 0 to show you that this function instance was really simultaneously executed 10 times. There were 10 instances of the same function with different variable depth. Variable depth, name depth, be more accurate. Being more accurate, name depth inside these instances was pointing to different objects. However, the same name can point to the same object. If I give the same object to function, then it will just use this particular object, something, or just something here provided here something. It's not really important, but I will show you ID of object depth, and you will see that identifier of object depth is different. ID is built-in function to check what is internal identifier of object in Python, and I will show you ID of these something here. No error this time. Okay, so call function, let's start from 5. From 5 to 10. It will take fewer rows, fewer lines. Okay, 6 is missing parameter something, so I'll put here something. I don't know what to put here. Voila. It's not really important what is here because I'm not using this object. But you can see that each instance of functions had the same link to the same object. So if you want to provide something to each level of recursion, to the deepest. You can just copy object in parameters, and it will give this function access to the same thing. So let's return to algorithms where recursion can be used. Typically, teachers tell about two algorithms: factorial and Fibonacci numbers. These are bad cases, both, because recursion is not good way to show factorial and Fibonacci numbers. But that's why usage of recursion in Fibonacci numbers especially can be used to show when recursion is not bad, is not good solution, and what is better. But today I want to give you some different and interesting algorithms. For example, let's create algorithm of calculating power of some number. Power of a number. You will tell me, oh, what's the problem with that? No necessity of recursion here, and I will agree with you, because solution is very simple. Just take number, float number, because it's not obliged to be integer. However, it can be integer, it's not very important. But I will use float numbers. Float of something taken from input. Some string from input, and float constructor will create me object from this string. Okay, and here in a variable I have now some number. Then I want to have power also from keyboard, for example. And then I want to call some function. Okay, answer. To call function, which I will create by myself, some function. I will name this function my power, and give this function two parameters, a and показатель and power. Okay, this function should calculate. So here I'm using this function as a black box, an, and waiting for answer. Okay, and print this answer. That is my use case. But what about the function? What about the function? First idea is to just multiply a by itself. Because what is a in power of n? It is a multiplied by a, multiplied by a, multiplied by it, and so on, multiplied by n one time again, and a should be multiplied by itself n times. So what's the problem? First idea is, let's create production with its initial state 1, and then for loop, for iteration in range n. So the body of the loop will be done n times, and p should be multiplied by a So p will be multiplied by a one time, second, third, and so on. And then I can return the result. Return p. Yes, it's the function. Def my pow. A n. Yes, it's done. Yes, of course. But let's try to solve this problem with recursion. Do you have any question? If you don't have question, switch your microphone off, Amar. If you have questions, ask now. Okay. But this is not a recursive solution. It's good, but let's turn from it to a recursive variant. Is it obvious algorithm? Can I just erase it from board? I'll erase it because I think that this iterative solution is too simple to be discussed. Am I right? I hope. Where is recursion here? Can't see. To have to program recursion, first of all, you should understand what is the task, and could be some subtask decomposed from the initial task. Yes, it's the case, because a in power of n from math is a multiplied by a in power of n minus 1. This is always correct, but really I want to use this formula only not to enhard my task, because if n is negative, then this formula will just provide me more complex power, minus, for example, minus 9, and here will be minus 10. Oh, it's harder to calculate. Let's try to return to 0. Why? Because a in power of 0 is very simple case. Any number in power of 0 except of 0 itself, because 0 in power of 0 is mathematical uncertainty, mathematical uncertainty. 0 in power of 0 normally will produce an error in Python, because it's like 0 divided by 0. Normally, without mathematical apparatus, we cannot operate with such situations. However, with mathematical analysis, if these zeros are not just zeros, but some successions which are going to some and limited by 0, then this can be solved. What is the limit of such succession with problem of 0 in power of 0? But normally it's not the case. Okay, let's talk about normal numbers where a is not 0. For other numbers, a in power of 0 is just 1. So it's not a problem. Okay? So I have two cases. Let's imagine that this case should be done when n is greater than 0. This is the case when n equals 0. I change it 0 to n, but I'm writing here that n is equal to 0. So these are two cases which can be separated by normal if-else operator. And what for this was done? Because this is subtask. I need to multiply only once inside my formula. So I can delegate calculation of such thing as a in power of n minus 1 to different instance of the same function. Because my function, my power, will solve such tasks. Okay? And I'm sure if n is greater than 0, I'm not assuming that n could be possibly lesser than 0. Now I don't have such formulas, I don't provide them, and it should be contract of my function. I will believe that that user is not treating me, is treating me well. Okay? So recursion algorithms start from math, from mathematics. We should understand that initial task is very similar to some slave task, some subtask. Okay? And here can be some additional steps to generate answer to the initial task, but some part is the same as initial, respecting parameter, of course. Calculation of parameter also should be done during calculation of recursive case. Okay? So, how this mathematical system, formula with system, should be interpreted, should be coded into code. Function my power, here a float of course, and n, which is integer greater than 0. It can be documented, but I will not do this because I'm lazy now and in hurry. So I want to differ these cases. And first of all, I need to check what is n. Let's start from the simplest case, from my mouse in quotes, from final case of recursion. If n equals to 0, then just return, what should be returned? Let's return 1. If really, if I'm sure that n is greater than 0, then here can be only else. But I will produce here if to underline that n is greater than 0. It is only to document it. I can write here else and this as a comment. But a comment which is checking the program itself is better. So let's check that n is greater than 0. In this case, I will return what? N. Oh, no, not n. A multiplied by, and here is the place to use recursion. Who will calculate a in power of n minus 1 for me? My function itself. It's me, myself. My pow will calculate this for me. A, and that parameter guarantees that this subtask is easier than my task itself. So I'm flowing to my final case of recursion. That's why it is guaranteed. Guarantee of this is in hands of programmer and in mind of programmer who should know math. Okay? And understand that yes, recursion will end. It will not achieve recursion maximum depth because we are not complexing, but we are not complexing task, but we are diminishing problems. Okay, let's make this program here. Oh no, I'll create script now. It's time to create program and to save it. Okay, so let's create function my power with a. Here I will print that it's float, n it's int. This my power should return float. So types annotation is used. Yes, if n equals 0, then return 1. Else, if n is greater than 0, then return a multiplied by my power a n minus 1. It's very important to understand that this parameter provides task that is really easier. Okay, here a from keyboard, n from keyboard, and answer from function my power. A and n are provided here, and print answer here. Okay. So my program is waiting for two numbers. First is a number to calculate in the base of my power, and the second is power itself. So 2 in power of 10 is 1024. Yes, it's true, and I can use my algorithm to calculate. I can use it here because it's already function is already defined. I can just call it from here my power, for example 10 in power of 100. Because of Python has long numbers, then my power will calculate this. Okay, and it's okay. But how many operations should be done to calculate this particularly? 100, of course. No, not iterations, but number of subcalls. And what if I want to calculate power of 1000? And what if I want to calculate 2 in power of... Oh, problem. Maximum. So, look. When I tried to calculate 2 in power of 2000, for Python it's not a problem to operate with such long numbers. You saw that yes, it worked, but problem was in recursion error. Recursion depth exceeded. It's bad. It's very bad. Because normal recursion depth is below 1000. yes, I can enlarge this number, this allowed recursion depth limit, but normally recursion should not exceed such limit. Okay, and the main problem here is not about recursion itself, but about number of calculations, because to calculate 2 in power of 2000s normally with such algorithm, or with our previous version with loop, with for loop, for I in range 2000s, I should use multiplication thousands of times. And what's the trick here? The main trick is to generate some interesting mathematical formula which will provide us better solution. How to reduce multiplications, number of multiplications. Look here. What you know about power? What if n is even number? What if n is 2 multiplied by m, where m is integer? What if this so? You should know that from math that it means that a in power 2 itself can be got in power of m. You can get it in power of m, and it will give you a in power 2 multiplied by m. Also, this can be interpreted as a in power of m and then in square. Which is better? What is better, this one or this one? I think that this case is more comfortable to me. A in square can be calculated very fast. A in square, okay. But first of all, look here. I will return that n is m is n divided by n. So I will print here n divided by 2, n divided by 2, n divided by 2. N is divisible by 2 because it is even number. Okay, but this version of formula is not interesting for me now. I will use this one. What is main idea? That task of calculation a in power of n can be substituted to the same task where something new, of course, because a in square, but this is also float number, should be calculated in some power. So calculation of a in power of n can be substituted by calculation of b in power m, where b is a in square, m is n divided by 2. Okay? What it gives? It gives us third case of recursion. Third case of recursion. When n is greater than 0 and n is even, n modulo 2 equals 0, I will use Python construction. N by modulo 2 equals 0, it's even number. In such a case, we can use this formula to reduce power. Reducing of power will give us simplifying of task. Task is more simple than initial one. Initial task was to have nth power of a, but here I am just over jumping to n divided by 2. Look, if I was to calculate a in power of 1, 2, 3, 4, 5, 6, 7, and 8, if my initial task was to calculate a in power of 8, then only with normal recursion case, I could simplify task only by 1. This task could be downscaled to this task, then here, then here, then here, then here, then here, then here, and then to a in power of 0, which is final case of recursion. Okay, so I have depth of recursion of even not 8 but 9 levels of recursion. Depth of recursion is 9, but I need to calculate this multiplication 9 times, really. No, 8 times. 8 times I need to calculate multiplication. But with such way of reducing power, I can reduce power from 8 immediately to 4, over jumping these cases. 4 is also even number. I'm over jumping here. Here it's not really important, but I can over jump here and here. So I have economy of not calculating now, but really here I'm not calculating anything. Oh no, yes, I should calculate a in square. A in square is also multiplication. But anyway, I'm just over jumping many cases which are not to be calculated at all. And the initial, you should understand that good recursion ideas go from math, not from a programming language itself. Okay? So, how to change my function? This case should be applied only if number is not even, if it's odd number. So this number is, I will reorder them. Final case will be first one. This case will be second, and this will be the last one in my succession of a leaf construction. So here I want to check if n is divisible by 2. N by modulo 2 equals 0. In such a case, I substitute task of calculation my power a in power of n to my power a in square. I'm using multiplication here. I'm not using normal power. It's frank. It's frank if we are creating our algorithm of calculation something in power something. It's I don't know other word. It's honestly not to use normal standard operator of power, even here when I'm calculating only a in power of 2. So I will use a multiplied by a. And here I will use n divided by 2. But I'm sure that n is divisible by n. The residual is 0 here. So I can and should use integer division. This division variant. Because in my function I imply that n is integer. And here I should provide to my function itself integer power. Okay? And else, of course, I imply that n is greater than 0. Let's not ask it here. Else, return normally a multiplied by my power of a in power n minus 1. Because here I already multiplied a in power minus 1 to a. Okay? This algorithm is fast power algorithm. It reduces number of needed calculations to logarithmic from n. Its asymptotics is O from logarithm with base 2 of n. And it's very, very good. I will not prove this. I'll just mention this. That its asymptotics is very, very good. Let's check. Let's program this algorithm. So here, I'm sure that n is greater than 0. To be sure, to be ensured, I can add assert here. Oh, I'm sorry. N greater or equal than 0. It's function contract. Use it with n greater or equal than 0. This is my self-produced error. I'm checking each time in debug mode. In debug mode, this assertion will be checked each time function executes. And then I can believe that it's already, then after this instruction, if code flow, if execution flow goes here, then I'm sure that n is greater, was greater or equal to 0. Okay, and work without checking other things. Okay, but what I want to do is check really that n is even number. So I'm checking that n modulo 2 is 0. And what should I return in this case? Just power of a in square, a multiplied by a, which is a in square. But n should be divided by 2 with integer division to remain integer. Okay, and this is really fast power calculation algorithm. We can check it, how it works, and it will work with very big powers. I will not use too big powers, but oh, I'm sorry, because this number was too big. I'm sorry, power. It was too big to be stored in floats. Floats are not so big. Now, I could change here float to int, because integers are just infinite in Python, because long arithmetics is built in Python. So let's check this with integer basis. So 2 in power of, for example, 10,000, and we have 407 lines of digits. Let's watch. And we calculated this by ourselves. It's not so easy to read, but what do I want to? I want to call the function and to store the result. Even with million, 2 in power of million, it's a very big number. Up! Lesser than a second. Lesser than a second. Whoop! No recursion limit was exceeded. Let's check. We will use a built-in power operator. Two in power of million with built-in operator star star. Yes, it also was calculated very fast. Very fast. But the main thing is, were we correct or not? Let's check. Is x equal to check x? I will not print these numbers because they are too big. But yes, we calculated this correctly. Okay? How many recursion levels were used to calculate 2 in power of 1 million? Let's check it with code. Now here, instead of returning 1, I will just, because it is the only final case. When n achieves 0, it returns 1, and then it starts to return back to the first level of recursion finally, and from recursion succession of recursion executions. So I want to just produce error here. On the last step, my final case will not return anything, but will produce error. It will give me a way to watch how many recursion levels were used. Okay? 2 in power of 1 million. Yes, 1 million. Yes, we have traceback, of course, but in this traceback, I can see not so many lines, not so many. They differ. That's why Python couldn't shorten this output, but we can calculate 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. 24 is not so great number because first case of recursion, and not only recursion, but our initial algorithm would really produce 1 million of multiplication operations. Oh, let's repair algorithm, and I want to send it to you because this proves you, this algorithm really proves you that recursion is good idea. Okay, that's, I will send you the solution just after lesson ends. That is the end of our lesson today. I'm leaving you with such interesting idea. I didn't use a standard variants of demonstration of recursion, and then on next lesson, yes, and today, know any recursion task, home task about recursion. Just try to lie it in your head. Just try to put the proper place. Maybe you should rewatch once again this lesson to understand everything. Also, try my examples. Try to create recursion function by your hands. Print it, type it symbol by symbol from video to check how it works, how function calls itself, how parameters are given. No any task for me to check you, okay, but you should work with this video once again, I think, if everything is not so clear, okay. But your home tasks are the same. You should I don't know, just to practice, just use check.io. Check.io will give you Python syntax practice to understand, and Google also will help you. Check.io gives you very good practice for simple tasks. Okay.